What time is it? It's science time.
Science time. Let's all stop and just unwind. 1, 2, 3, 4, here we go. Learn so much your brain explodes. Lessons so cool, so fresh. Beat so big you'll lose your breath. Learning facts and real cool stuff. Scream for more, can't get enough. It's science time. It's fun, you best believe. Explore and learn new things. Come and join me, please.
I'm Mr. C, and this super smart group is my science crew. Lila is our notebook navigator, Alfred is our experiment expert, Riley is our dynamite demonstrator, and London is our research wrangler. Working with my team is the best and makes learning so much fun. Actually, you should join us. Today, we're talking about sound and vibrations. What time is it? It's science time. It's DIY. It's science time. I'm Mr. C. Come join me, please. You're part of my science crew. Welcome back to DIY Science Time. Today we're talking about sound, and we're going to make some noise. In fact, right now, put your hand right here on your throat and go la 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 la. Can you feel that? Can you feel that vibration right there? You know, vibrations are all around us. In fact, I have a xylophone here. I want to play a little tune I've been working on. Do you recognize that? It's science time! So the question is, what do vocal cords, a xylophone, and noise all have in common? Vibrations. That's right, today we're talking about sound and vibrations, and you'll need a couple of materials to follow along.
It sounds like we're going to build a wave machine today. That means we're going to need a few materials to get our activity rolling. Gumdrops, duct tape, wooden skewers, and you know what's music to my ears? Our totally tubular science notebook.
A science notebook is a tool that every scientist should have, and it gives us a place to record all of our learning. Taking good notes and being organized allows us to be better scientists. A science notebook allows us to go back and review all the data and information we've gathered during our experiments. Plus, it allows us to share results with other scientists who might be interested in learning more about what we've discovered. Whenever you see the notebook pop up on the screen, like this, it's a reminder that this is a good place for us to jot down new information. You can see I've already added a title and a list of materials for today's activity. Our crew is still going to have lots of information to collect and organize as we go through the experiment, so keep your notebook handy. Most importantly, the more you use the science notebook, the better you'll get at taking notes and recording data. If you don't have a science notebook yet, download a copy of Mr. C's science notebook from the website.
Sound is a form of energy, and I can take this, a tuning fork, and illustrate that. When I strike the tuning fork against this rubber pyramid, you get a beautiful sound. That's because these tines are vibrating. When I stop the vibration, the sound stops. But sound is super difficult to see because we don't see it. So what I want to do is show you that sound has energy, and I want to show you this with this cup of water. So, did you hear it? Let's do it again. It's like, it dampens the sound. The water slows the tines from vibrating, and it causes it to stop. And once these stop vibrating, each of these tines, when it stops, the sound vibration stops. Now, we can show you another way that sound has energy by using this ping pong ball. I'm going to slide this here to the center. I'm going to strike this again. You can see the tines are actually vibrating, kicking back and forth, and that's what causes that ping pong ball to shoot off to one direction. I want to try it again. I want to get it to shoot really hard. That is so cool. So sound is a form of energy. We can hear the sound, we can feel the sound, but most importantly, we can experience and love the sound because it's all about vibrations. All sounds are produced by vibrations, and all sounds have this origin. A vibration is a rapid back and forth motion that creates disturbances. For example, when I strike this tuning fork, the tuning fork vibrates back and forth repeatedly. This creates vibrations, which create sound waves that travel to our ears, and then our ears transmit that signal to our brain. When I stop the tuning fork, the sound stops. No vibrations equals no sound. Just like dropping a pebble into a pond, vibrations travel in all directions from the source. Isn't that amazing? That sound is so beautiful, and it's a sound and song we're all familiar with. But how does it work? Inside of here, there's something magical. It's a music box. And this little music box, well, let me take one apart for you to show you what it actually looks like. This is so neat. It has this drum, and it has these little pieces that as it spins, what happens is those pieces hit these little forks. It looks like a little comb that's made out of metal. And every time those bend and they vibrate, they produce a sound. And each one of those, because they have a different length, produces a unique different sound. And that is how we get to play Happy Birthday. Now, when I get this spinning, you can change the speed of it. Just like that. But what would be really cool is if you could actually make your own song. And in fact, I have a music box that I purchased, and I drilled it onto this extra piece of wood I had at the house. And basically, it's the same thing. It works the same way. I have this sleeve of notes, and I punched out the holes. So this one tells the music box to play on certain notes. And this is what it sounds like. Let's see if you can recognize it. Oh, that's not part of the song. That's just it getting set up for the song. Did you recognize it? It's science time! Bum, 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 bum. But what's really cool is we can take this idea with these little teeny tiny things here, these little forks, these metal forks, and we can actually make an instrument ourselves using a meter stick. You want to give it a try? All right, check it out. I have my yardstick or meter stick, but we're going to use the yardstick today because it has bigger numbers and allows you to kind of follow along a little bit better. I also built this contraption, and this is going to represent a tabletop. So you can do this on a tabletop just like this, and you can vibrate it, but I'm gonna do this here because I want you to be able to see what's happening and actually see the vibrations as they change. So our music box, if you remember, had those little tines that were vibrating as the drum and barrel was rolling. Bing, bing, bing. And that was causing those little fork-like pieces of metal to vibrate. Well, we can replicate that with this contraption. So I'm gonna start right here. I'm gonna take this yardstick and have it hanging off about 21 inches, and then I'm just gonna pull down, and I want you to listen to what happens. Did you hear that sound? It was a low sound, right? So we can do that again. And now, if we shorten that about a third, I went from 21 inches to 14. Now, we're going to create a different sound. We're going to produce a different pitch. And the question is will it be higher or will it be lower? Are you ready? You have your prediction? Let's give it a try. definitely higher. Ring. And you might be wondering to yourself, how does that actually work? Well, a couple things are happening. When it's out here like this, there is more yardstick to vibrate. There's more material. And if there's more of something, it's harder to move it. And so when I have less to vibrate, it's going to actually move faster. So the question is if I split this in half again and go down to 7, what'll happen? You ready? Let's give it a try. So it's vibrating very quickly, and you can hear that the pitch is really high. So I can go. I can even stretch it out even further. And you can physically see that it's vibrating slower. But you can have fun with this. You can. Did you hear that? Oh, that's so cool. The pitch is increasing. Oh, that's so neat. So I only have one of these. I can actually try to make a tune. So maybe, oh, that's, did you hear it? I was trying to play It's Science Time, but I'm not sure how good that sounded. Forgive me. But you can make one of these also. You can make your own piano ruler with a meter stick.
Ever wonder how a record player works? A stylus touches the top of the record and rides around the disc. It picks up vibrations that are then sent to a cartridge, and the cartridge converts them into electrical signals. These signals are sent to an amplifier which converts the signals back to sound, which is sent through the speakers. Now that's music to my ears.
This next experiment will blow you away. Grab 2 balloons, a penny and a hex nut. Put the penny into one of the balloons and the hex nut into the other balloon. Carefully inflate each of the balloons. Now rotate the balloon in a circular pattern to get the penny spinning on the inside of the balloon. Do you hear anything? Now take the balloon with the hex nut and get the hex nut spinning inside the balloon. Wow, it's so loud. The hex nut's edges aren't smooth like the penny. The 6 edges on the hex nut create vibrations, which create this unique and loud sound. Speed it up and slow it down to change the pitch.
I've got a spoon-sational experiment you have to try. Tie a 3-foot piece of yarn around the end of a spoon. The spoon should hang freely from the string. Next, wrap the ends of yarn around your finger and place your finger into your ear. Have someone in your crew take another spoon and gently tap the suspended spoon. Did you expect to hear something? Isn't that sound simply amazing? The vibrations created when the spoons tap each other travel through the string, up through your hand, and into your ears. I wonder what happens if you use different string or something other than spoons.
We know that sound is a form of energy, but did you know that sound travels in waves? That's right, sound travels in waves, and we're going to build a wave demonstrator to illustrate that concept right now. What you're gonna need is to pull a piece of tape. I'm gonna make mine 36 inches. You can actually make it longer. And then I'm gonna turn it upside down on my table. It's sticky. It's really sticky. Ah! All right, I made it extra long so this works out. Oh, it's so sticky. And now what I'm going to do is I'm going to take another piece of tape and tape this down to hold it in place so that it doesn't move. We're going to be using skewer sticks and gumdrops for this. Now what we're going to do is I'm going to slide this out just a little bit. We're going to be taking a skewer stick and placing it 1 inch apart all the way down. We're gonna space it 1 inch. Ding, 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 ding. And in theory, we should have 36 if we're doing 3 feet. All right, so, but that's not going to be enough. We need some mass to allow the Wave Demonstrator to work properly, and that means we're going to take these gumdrops and put them on each side because we want it to be balanced. So I'm going to push until I feel it so that they're on exactly the same amount every time. And then I'm going to place that right here at the 1 inch mark. And it's going to lift the tape up a little bit. Now we repeat that process 35 more times. Let's go. And 36. So we have all 36 skewers with the gumdrops on the sides. Now comes the tricky part. We need to get another piece of tape on top of this to cover it. Now, you don't have to do this, but it definitely will keep things in place if you get it on there. All right, here we go. All right, so now we have it. And now what we need to do is hook it up to this. All right, so it's nice and tight. And now the reaction when I hit this, let's get it to settle down. Here we go. Oh, that's so cool. The harder I hit it, the bigger the wave. And you can see the crest. That's when it's at its highest point. It's going up. And it's coming across. It's losing quite a lot of energy. I'm thinking if I had a longer demonstrator, it might actually work a little bit better. But here's the thing, you can make your own demonstrator very easily. And how you do this is going to determine how the wave works. Maybe spreading them apart farther will allow it to work differently, and you can see the wave a little more dramatically. But we're gonna try it from this side. I'm gonna try from this side right here. Oh, yes. There we go. You can see that the wave goes across and then it comes back and it bounces again. It likes this side better. Oh, sweet. Literally, sweet. And I can actually get it. Okay, so I think I figured out how to make it work better just by playing with it a little bit. I was flicking it here. It works okay, but if I just take this and I give it a quick twist, you can see that wave all the way through it. Oh, that's so awesome. Wave Demonstrator. Build one, have some fun, explore sound, but most importantly, just sink your teeth into this experiment. Sound, vibrations, everything!
When a guitar string is plucked, the vibration travels from the bridge of the guitar and resonates throughout the top of the guitar. The vibration is also transmitted to the sides and the back of the instrument, which then vibrates the air in the body.
That vibrating air comes out of the hole in the front of the guitar, and we hear it as sweet, sweet music.
Let's continue exploring sound with a simple bottle experiment. We can take a bottle and make it into an instrument very simply. How? Check this out. I have an empty bottle here. When I blow across the top, it produces a sound. It produces that low pitch. If I take this bottle that's filled with water, that's super high pitched. I'm gonna dump out a little bit so we can get maybe a note. Let's try it again. Yes. So, did you hear a difference? I did. And the thing is this bottle here was completely empty. And when I was blowing across the top of the bottle, I was vibrating the air inside of this bottle. And this bottle has a lot more air in it than this bottle. This bottle has an air column that is about this tall. This bottle has an air column that is this tall. More air, it vibrates more slowly. More air vibrating more slowly gives us a lower pitch. Less air vibrating faster gives us a higher pitch. And here's what's fun about this. If you have more of these, you can actually make an octave, and that means you'd have 8 of them. Octo, 8. So you can make like a xylophone, a bottle xylophone, and you can make songs and play music and have fun. Or you can take the single bottle, get some water out of it. I emptied the water. The air column just got larger, so our pitch should get lower. Let's give it a try. Let's take some more water out. Little more. And if I empty it anymore, I have this one, which is it's your turn. Give it a try. Your turn.
Are you ready to build your very own kazoo? Grab 2 craft sticks, 3 rubber bands, and a straw. Stretch a rubber band along one of the craft sticks. Now carefully cut 2 pieces from the straw. Place 1 piece of straw under the end of the rubber band so that the rubber band is slightly lifted. Place the other piece of straw on the other end of the craft stick on top of the rubber band. Then sandwich everything together with the second craft stick. Wrap the last 2 rubber bands around the ends of your craft stick sandwiches to hold everything together. Once it's all held together, blow through your kazoo. That sound is so much fun!
Ready to create an out-of-this-world sound? Grab a Slinky and securely place a styrofoam cup onto the end of the Slinky. Carefully stretch the Slinky and tap the Slinky with your finger. Did you expect that sound to happen? Would the sound change if you use a pencil or a pen instead of your fingers? You've created yourself an out-of-this-world sound that can be used for sound effects.
Have you ever wondered what the difference is between a fish and a piano? You can't tune a fish! The crew has been busy today and we've heard lots of different types of sound vibrations. And that's the most important thing to remember. All sounds are produced by vibrations. I noted that when an object vibrates faster, it produces a higher pitch. And when it vibrates slower, it produces a lower pitch. The Wave Demonstrator, the hex nut balloon, kazoos, guitars, ruler pianos, they all use vibrations to produce sound. I really like the space sound the Slinky made. Do you think we could make other cool sound effects? I think talking in a can, like this, sounds like a robot. We are science robots. We love science. Do you think you could apply some of the things we worked with today and engineer your very own musical instrument? Give it a try and have some fun making music with your science crew.
Hey, what an amazing day! The sweet, sweet sounds of science. And when it comes to science, nothing sounds better than learning with all of you. Wasn't today amazing? We talked about vibrations which make sound. Tuning forks, musical boxes, musical bottles, and your handy dandy science notebook. That's right, this notebook is something you need to take notes in so that you can go back in the future and see all the experiments you did with sound. And if you don't have one yet, hop online and download it. Well, what can I say? So much fun. And on that note, keep learning, keep having fun, keep exploring, and remember, science is wherever you are. See ya. Bye.
It's science time.
That's too hard.
I don't know.
It's science time.
Tuning forks. What's that thing called? Make sure you hop online and download one. It's hitting my finger.
It's so much
La 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 la. La 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 la. Whoa!
science time. Yes,
Oh my gosh, that scared me.